So, without further ado, welcome Adam.
Okay, thank you very much for turning out. I know that Obama is on the other channel, so thank you for tuning in. As I said in the abstract, general relativity really is the perfect theory. You start off with some simple thought experiments about if you're a beetle wandering around on the surface of the sphere, or thought experiments about people falling in elevators, or as we see buckets whirled overhead. And before you know it, you have reconceptualized nature's most familiar force. And that's a reconceptualization that really achieves almost immediate, Aldrin's invented, decisive experimental confirmation. And not only does general relativity, this reconceptualization, tell you about the things it was designed to tell you about, namely planets and the solar system, it also tells you about the origin and fate of the universe. As well as being, well, I should say, I think that it really is the perfect theory, and there's not anything else in all of science that really hits all of those high notes all in a row, all those perfect elements, with, I think, the possible exception of the theory of evolution. Certainly in physics, I think it is the most sort of perfect canonical example of a scientific theory that we possess. As well as that, it has a reputation for being hard. And it is somewhat hard. It took no lesser a mind than Einstein's 10 years of full pursuit before he invented it. And I don't have 10 years during this lecture. I don't even have the 10 weeks that it takes in my graduate class to explain general relativity. But the surprising thing, I think, is actually not how hard it is, even though it is famously hard. It's really how easy it is. It's one of these wonderful things about science, that things that were once very hard, and only one famously intelligent guy was able to understand it and conceive of it, get better and better understood. We come up with more and more powerful ways to understand these things. And eventually, the level at which you have to be in order to comprehend it goes down lower and lower and lower, until we reach today, where I think, while you're not going to understand general relativity perfectly, I hope I can get over the essence of it in this one hour. Really just a little bit about the history, a little bit about why we believe it, but most important of all, just the one central idea that makes it up, that's in some sense embodied by this vacuum chamber picture of a feather and a bowling ball competing and coming to a dead heat as they fall. We have some advantages over Einstein in trying to understand it. And the first advantage is that Einstein came first, and therefore made all of the mistakes that it's really possible to make en route from this observation that the bowling ball and the feather fall at the same rate to the theory of general relativity. And really showed us the way not to do it, and therefore the way to do it, to understand this fact. Obviously, in today's talk, I'm not going to do the maths. In fact, I promised that no science background was needed. I'm not sure, well, I will have a little bit of maths. I've given myself a budget of 6 equations that I'm allowed to show you through the course of the lecture. Nevertheless, if you don't understand those 6 equations, I actually think the diagrams do it all. If you've not seen the 6 equations before, and if you don't understand them, just don't worry about that. The concept is actually, in some ways, even more simple than the equations that require it. In fact, Einstein even had a little quote on this topic. You can see that? Demonstrating that, as well as inventing the general theory of relativity, Einstein also invented the humble brag.
Don't mind me.
Good. So, before I tell you what general relativity is, I'm going to tell you what general relativity isn't. And the thing that general relativity isn't, amongst other things, is special relativity. Uh-oh.
We can see.
Oh, bollocks.
We're okay.
This general relativity, it would say, is not equal to special relativity. That is an inequality rather than an equation, and therefore does not count against my 6. General relativity, special relativity and general relativity both involve the word relativity, and were both invented by Einstein. However, they were invented 10 years apart, and really special relativity, the first one, special as opposed to general, special means only applies in a certain case, general means applies more generally. Special relativity was invented by young Einstein in 1905 when he was 26 years old. General relativity was much harder and had to wait until Einstein had got older and shrunk. And special relativity, which I will not be talking much about today, can be sloganized as the statement that nothing can travel faster than the speed of light. That the speed of light is a universal speed limit that bounds the rate at which anything can move. And to very briefly sloganize general relativity, general relativity says that the same applies to gravity. In fact, special relativity, even though we said nothing, which is a sweeping, expansive statement, didn't obviously apply to gravity when it was first formulated. And general relativity is an attempt to take this idea, this powerful 1905 idea, that nothing can travel faster than light, and apply it to the gravitational theory, with which it seems to be, at first, inconsistent. Okay, so let me tell you, or remind you, that there are 4 forces, we believe, in nature that describes absolutely everything we see. 4, I should say, fundamental forces. And those 4 forces are electromagnetism, which describes the electric and magnetic forces, in fact describes almost all the non-gravitational forces that you know and see around you. Now there are actually 2 more in addition to electromagnetism at the top of this list that Einstein didn't know about, but we do, and those are the strong nuclear force that describes the interior of atoms, of atomic nuclei I should say, and the weak nuclear force, which is another force that also describes the interior of atoms, and under certain circumstances is weaker than the strong nuclear force. And then in addition to that, there's gravity. Now Einstein actually only knew about the first and the last of these, but nevertheless, we can ask to which of them does Einstein's theory of special relativity straightforwardly apply? And the answer is it's the first 3 of these. Electromagnetism has a speed limit built into it. In fact, the level of intellectual progression is in the opposite direction. The way that Einstein came up with this theory is that he noticed that baked into electromagnetism was a symmetry that no one had noticed before, even though electromagnetism in its modern formulation had been around since Maxwell's equations 50 years previously. What Einstein noticed and led to his 1905 breakthrough, special relativity, is that baked into electromagnetism is a symmetry, and that symmetry means, amongst other things, that nothing can travel faster than light. And indeed, not only does this theorem apply to electromagnetism, it also straightforwardly applies to the strong and the weak forces. However, it doesn't look like it applies to the gravitational force. Looking at it, it looks like gravity, as described by Newton, in fact, does have a speed limit. Doesn't have a speed limit, I should say. So I'll remind you a few facts about Newton's laws. Newton, Sir Isaac Newton, wrote down these laws in 1687 that describe gravity. They describe why objects fall towards the floor and why planets fall towards the sun. And one of these laws, his first law, says that objects on which you do not exert a force move in straight lines. Force-free objects, objects not subject to force move in straight lines. That was Newton's first law. And we'll actually see that Einstein's theory of general relativity respects that. It will still remain true that objects not subject to a force move in straight lines. However, we're going to have to understand in a new context exactly what we mean by force and by straight. Newton's second law is also our first equation. And that says ma equals f. Let me describe what that is in words if you've not seen it before. That tells you that if you take an object and exert on it a force F, you will cause that object to accelerate. So the first law is really just a special case of the second law. The first law says that if there's no force, the acceleration is 0 and things move along straight lines. The second law says that if there is a force, you get non-zero acceleration, and it's given by this expression. This, in fact, will also, properly understood, be true of general relativity, of Einstein's theory of gravity, as well as Newton's theory. The third Newtonian law is his law of gravity, and this is the one that's not going to be true. This tells you about what is the force produced by the gravitational law, and the rule is this. It's his celebrated inverse square law, which you may or may not have seen before. And it looks like that. What this force law tells you is that if you have two bodies, one of mass big M, let's say the sun, of mass big M, and the other of mass small m, let's say the Earth, these two bodies will have an attractive gravitational force between them. An attractive gravitational force whose strength falls off like the distance between them squared. This is the famous inverse square law of Newton, with which he successfully modeled the solar system. It will turn out that this one is the one that will require modification due to general relativity, that Einstein, in fact, jettisoned. In fact, you can immediately see that there is some tension between Newtonian gravity and special relativity. Special relativity says that nothing can travel faster than light, so that if I wiggle something over here, I can't find out 8 light minutes away, let's say, at the location of the sun, that I wiggle something over here, until 8 minutes have passed. By contrast, Newtonian gravity doesn't seem to respect any kind of speed limit. In Newtonian gravity, the force produced by a point mass, the gravitational force produced by the sun, let us say, on the Earth, is just given by this formula, and that force propagates instantaneously. So if the sun blew up, we wouldn't find out about it through light for 8 minutes, because light cannot travel faster than light, which is tautologist when he said it like that. By contrast, gravitationally, at least according to Newton's law, we would know about it immediately. We'd know about it immediately because the right-hand side of this would change, because the mass of the sun would change its distribution. And consequently, the force exerted on the Earth by the sun would change. And then you can test the exertion of that force by seeing how objects accelerate. So this is a problem. This is a problem. Newtonian gravity, as told to us by Newton in 1687, seems to be inconsistent with special relativity, as told to us by Einstein in 1905, and one of them has to give. One natural alternative might be to give up on special relativity. It is, after all, at this stage, only 10 years old. However, Einstein had invented special relativity, and he was not keen on option 1. So he took the more radical option 2, which is to give up on, or rather modify, Newtonian gravity. It would not be inconsistent if it turned out that this principle that nothing can go faster than light only applied to light, the electromagnetic, the strong and the weak forces, and did not apply to gravity. Nevertheless, it would be somehow deeply disappointing if we went to all that effort to get rid of the ether and show that nothing can travel faster than light, only to have to reintroduce an absolute notion of rest and reintroduce the notion of no speed limit in the case of gravity. So, this is the problem. How do we make the theory of gravity consistent with this principle that nothing can travel faster than light? We want it to be the case that one cannot make a telephone with which you can communicate on the other side of the universe using gravity. That you can't have an extremely expensive telephone that by blowing up stars on this side of the galaxy, you can tell someone on the other side of the galaxy immediately what's happening. That would be inconsistent with special relativity, but Newtonian physics seems to imply it. And at this stage, let me make a comparison. And the comparison is with the electrostatic theory. I'm going to spend one more of my equations, in fact, writing down the rule for electrostatics. And this is the force produced not by the gravitational interaction of two bodies, but by the electric interaction of two bodies. If you just have a charged particle here and another charged particle here, and one charged particle is of charge big Q, and the other charged particle is of charge little q, then the law of electrostatics, as told to us by someone in the 17th century, said that the force is given by this expression. It's an inverse square. If you have a positively charged particle and another positively charged particle, the force between them falls off like the distance squared, just like gravity. Now, electrostatics also looks like it's incompatible with special relativity. It looks like if you change the distribution of the force of the charges at a certain point, then immediately at some other point the force will change, and you can build a telephone just by jiggling electric charges. That's actually not true, and the reason it's not true is that even though this is the force law when everything is static and not moving, if you start jiggling things, the law changes. The rule changes, in fact, in a way that was well known already by the middle of the 19th century. It was known to Maxwell, and in fact it changes. Electrostatics gets generalized to electromagnetism that does embody this principle, that nothing can travel faster than the speed of light. So that suggests one obvious thing, which must have occurred to Einstein and all the others, is they said, I know, we'll just do exactly the same thing for the Newtonian gravity force law, that we did for the electrostatic law. You have an inverse square law, a force that falls off like the distance these things are apart squared. Why not just do exactly the same thing to electrostatics that Maxwell did to make it consistent with this principle to Newtonian gravity? And there's a reason that even though that looks like a very promising idea, it actually doesn't work at all. And the reason it doesn't work at all is a subtle difference between Newtonian gravity and electrostatics. And the subtle difference is this sign. Newtonian gravity is actually unlike the other three forces. In fact, gravity at all is unlike the other three forces. It's unlike electromagnetism, the strong force, or the weak force. And the thing that's different about it is this sign. In electrostatics, or in fact parallelly in the strong and the weak forces, if you have a positive charge and you have another positive charge, they repel each other. You put a positive value of Q and another positive value of Q, an electron and an electron, a positron and a positron. Those two have an electric repulsion from each other that moves them further apart. By contrast, Newtonian gravity, if you have two like charged masses, you have a positive mass and a positive mass, the Earth and the Sun, those two attract each other. This turns out to be an extremely significant difference. An extremely significant difference that means that gravity will not be anywhere near as easy to fix as the other three forces are. It will make it much harder to make it consistent with this special theory of relativity, that nothing can travel faster than light. It's a bit hard to explain exactly what goes wrong, but that crucial sign difference underlies the whole difference between the gravitational force and the other three forces, and really mean that it's of a completely different character. Okay, that's statement one. Statement two, comparing electrostatics to Newtonian gravity, is there's actually something funny about Newtonian gravity. In electrostatics, if you have two particles, say a positron and an electron, they have two relevant properties. One relevant property is that they have a charge. The charge tells you how strong a force they feel and how strong a force they exert, how strong an electrostatic force they exert. An electron also has a mass. The mass tells you how good it is at resisting forces. If it has a small mass, it is bad at resisting forces, and even a small force will cause a large acceleration. If it has a large mass, it's very good at resisting forces. That's why mass is sometimes called inertia. The property of having mass is the property of resisting the accelerative nature of forces. It gives you inertia and stops you being accelerated. By contrast, in Newtonian, and those two properties, namely the charge, the thing that causes the force, and the mass, the thing that resists the force, are two different things. And they can be completely different for different particles. A proton and an electron have a charge, an electric charge, that is of the same magnitude, but they have masses that's a factor of 2,000 apart. A neutron has the same mass as a proton, but it has no charge whatsoever. It has zero electric charge, while a proton has non-zero electric charge. In other words, in the electric force, for a given particle, this Q, the charge, the electric charge, and this M, the mass, the inertial mass that's resisting changes of motion, are completely uncorrelated. They're just two different properties. For a given particle, they have two different values. However, that's not true in gravity. It's already not true in Newtonian gravity, but the fact that it's not true in Newtonian gravity is kind of an accidental fact, whereas we'll see that it's going to be baked directly into the structure of Einstein's theory. In gravity, the mass, which is the inertial mass, this mass that lives in the second law, Newton's second law, that resists the acceleration caused by forces, is exactly the same object and sort of has the same role as charge of the gravitational force. So you can see that the analog in electrostatics of charge is mass, and that's the same m that's sitting there in the second law. So sometimes people call this m gravitational. The idea is that the m sitting here is like the charge under gravity. It says that if there's a gravitational field, how much force do I feel in it? How much does that get pushed on me? And we call that m gravitation. And the extraordinary thing is that for every particle we've ever seen in nature, the gravitational force is the same as the inertial force. The m that's sitting in this equation, the m that resists the impulse to move under a force, is exactly the same m as sits in here in the Newtonian, as the charge of Newtonian gravity. That is an experimental fact, but in Newtonian physics, it's just kind of a weird coincidence that it's the same mass that sits in both of them. It's an experimental fact, however, that we now know, that even in Einstein's time, they knew it to 1 part in 10 to the 11, and now we know it to 1 part in 10 to the 15 by experiments that look a bit like this. Just more sophisticated versions of this experiment. This is the world's largest vacuum chamber. It's a NASA facility in Ohio. And they have taken this extremely expensive vacuum chamber and done an old-fashioned experiment. They have taken a bowling ball and a feather, and they have released them simultaneously. And what they find is that, obviously not when air resistance exists, but in the vacuum, they both fall at the same rate. And they both arrive at the bottom at the same time. This is an idea that was said. Galileo is reputed to have done this experiment off the Leaning Tower of Pisa and achieved essentially the same result. And the reason why for that result is this fact, that the gravitational mass is equal to the inertial mass. That means that if you ask about the acceleration caused by gravity, the force is proportional to the mass, but the resistance to the force is also proportional to the same mass. The gravitational mass, which causes the force of gravity, is equal to the inertial mass that resists it, and that means that these objects will accelerate at the same rate no matter what their mass, because the mass cancels between these two formulas. As I said, in Newtonian physics, that's just a coincidence, or rather, it's a contingent fact. In Einstein physics, in General Relativity, Einstein was able to sort of grasp onto this as an essential fact that's actually going to be the key to uncovering the true nature of gravity. He said, can I come up with a theory in which this is, which is sometimes called the equivalence principle, that these two quantities are equivalent to each other? Is there some, can I come up with a theory in which that has to be true? That's sort of forced on you by the nature of the theory. Another way in which gravity is really not the same as the other forces is that it has this property. And the answer is yes, eventually Einstein did it, but it's actually a bit... his insight was that this was an important question to ask, and also that actually there is a way, there is a kind of force in which the inertial mass is equal to the charge under that force. We've seen that's true of gravity, but there's a whole other class of forces for which this is automatically true, and there is no mystery about it being true. And that class of forces is the so-called inertial forces, or fictitious forces. And so this is, I have a demo that goes along with this. We actually didn't have time to try this demo out, so this is, we're doing it live. This bucket is full of water, and if this works out, but we'll see whether it works out. So,
Wasn't a warning as
no, that's it. Should have got a free picture. So the idea is that there's not really any mystery about the way the water is staying in the bottom of the bucket now, because the force of gravity is acting down and is keeping the water in the bucket. The question is, why does the water stay in the bucket if it doesn't loop the loop? And the answer to that question is it's the centrifugal force that keeps it in. Or at least that's one way of phrasing the answer to that question. The water in this bucket can actually be looked at from two perspectives. One is the sort of our perspective as we just sit here. And from our perspective, it's clear why the bucket, the water isn't falling out of the bucket. From we who are not spinning with the bucket, the explanation is that the water wants to keep moving along in a straight line. But according to Newton's first law, until a force acts on it, it'll just keep moving along in a straight line. And furthermore, even when a force acts on it, it can only accelerate by a certain amount due to that force. And so for that reason, the water doesn't fly out of the bucket because it has to accelerate very rapidly down in order to fly out of the bucket, and by that time the water has already gone around and there's not time for it to fall down. That's our perspective. There's actually another perspective that we often use to explain this, which is the perspective of the centrifugal force. And there we don't align ourselves just sitting here. We imagine instead that we are with the water flying round in the bucket as the bucket goes round and round. And if you've ever gone round a corner sharply in a car, or any other number of situations like this, you will know that you experience what feels to you like a force that if you are in an accelerated vehicle, and the force tries to throw you against the turn. So if you lived in this bucket and were going around with the water, your explanation for why you didn't fall out would be that there is a force pushing you to the bottom of the bucket. That force is called the centrifugal force. And the formula for it is as follows. The centrifugal force that tells you that if you're moving with velocity v and being twirled in a circle of radius r, it tells you that the strength of the force that you feel that's pushing the water to the bottom of the bucket, that centrifugal force that's going through there, the strength of that force is given by mv squared over r in the radial direction. And the thing to note about that centrifugal force is that this force also has a charge that is proportional to the inertial mass. These fictitious or inertial forces always have a charge that is proportional to the inertial mass. But there's really no mystery for why the charge is proportional to the inertial mass in the case of the centrifugal force. For the centrifugal force, the reason that the charge, the force that the water feels, is proportional to its mass, and is proportional to the inertial mass, is precisely because the force is produced because the inertia of the object wants to fight the acceleration. In other words, it is precisely the desire of the inertia of the water to move in a straight line that produces this force when we make the water not move in a straight line. Forces like this are called inertial forces. Sometimes people call them fictitious forces because they're not sort of derived from one of the fundamental forces of nature, but are just made because you're in an accelerating frame of reference. Other classic examples of inertial forces are the Coriolis force, the centrifugal force, and there's a number of other examples of well-known inertial forces. The absolutely crucial thing is that for an inertial force, there is no mystery that the charge under that force is proportional to the inertial mass, because it is the inertial property of mass that forces the force to exist. Good. So, this was Einstein's #1 insight. He said, for inertial forces, it is guaranteed that the charge under that force is given by the inertial mass. And so his big question, his big insight, the big question that Einstein asked is, I'm running out of board, so I think this will better be the last thing, was, could gravity be an inertial force? Could it be a fictitious force? If it was an inertial force, if it was a force caused just by the fact that you are not really moving in a straight line when you think you are, that would automatically explain the equivalence of these two notions of mass. It would automatically explain why the charge under the gravitational force was equal to the inertial mass. But this is a pretty radical proposition. It's a pretty radical proposition because it requires us to be wrong about what we think are straight lines. Inertial forces arise when you make objects move not in a straight line. Nevertheless, we think that this chair sitting here on the floor is moving in a straight line in space-time. It's just sitting there, but nevertheless it's experiencing gravity. By contrast, if I take an object and throw it up and then have it fall, we know that while it's free falling, it doesn't experience the force of gravity. But inertial forces should apply to things that are not moving along straight lines. So, in order for Einstein's intuition to be correct, in order for gravity to be an inertial force, that would mean that we have to be wrong about what straight lines are. That means that a chair sitting on the surface of the Earth has to be not moving along a straight line in space-time, whereas a freely floating pencil that's thrown up and then falls down, or for that matter, astronauts orbiting in the International Space Station, or anyone else who is in free fall and not experiencing the force of gravity, has to be moving along a straight line. That sounds like a big ask, essentially. It requires you to believe, if you draw a space-time diagram, that topless Einstein, sitting in his deck chair, just sitting there for a great length of time, as he moving through space-time in this way, that this is in fact not a straight line through space-time, and the fact that it's not a straight line, you know because he's experiencing a gravitational force. We have promised that gravity is an inertial force. You only experience inertial forces when you do not move along a straight line. Therefore, we must believe, if we believe that gravity is an inertial force, that topless Einstein is not moving along a straight line, whereas the baseball, forming a parabola, that in fact is moving along a straight line, because it's in free fall and doesn't experience gravity. So this is the idea. This was Einstein's central question, following on from this experimental observation that the gravitational mass is equal to the inertial mass. That would be automatically explained if gravity were an inertial force, just like the centrifugal force, or just like the Coriolis force. But to believe it, it requires us to believe this extraordinary thing, which is that lines that we are accustomed to thinking of as bent, like the line formed through space-time by a thrown baseball is in fact straight, and Einstein is moving through a bent line through space. And now let me explain why the only way that this can be true, the only way that, that this radical notion of straightness, shall we say, that Einstein is asking to us to accept, can only be true if space-time is curved. This is where the curvature of space-time comes in. And to help you by that, let me remind you of something that you see on the back of your airplane seat, or at least the back of the person in front of you's airplane seat, when you fly across the Atlantic. But before that, I should mention that we have this force, that's the force of gravity, but we want to claim that that is a fictitious force. And this is what you see, if you tune to the right channel. You see the Earth, or rather, you don't see the Earth, you see a representation of the Earth. You see a map of the Earth. This map is called, anyone know what this map is called?
Mercator projection.
Very good. Where did that come from? Good. Yes, the Mercator projection. The Mercator projection is not, in fact, the Earth. It's a projection of the Earth. And it's a distorted projection of the Earth. The reason that it's a distorted projection of the Earth is you're trying to take a curved space, like the surface of the Earth, which is a sphere. I hope you know that it's a sphere. And if not, we'll have to have another red talk on that. It is a curved space, and you're trying to squish it down and pretend that it's flat. If you do that, there are inevitably going to be distortions. You cannot squish a curved space down to a flat space without introducing distortions. The Mercator projection was a particular choice made by navigators as a trade-off about what kind of distortions they were happy with and which they weren't. The biggest distortions are near the poles, the North and the South Pole, and the Mercator projection would lead you to believe that Greenland is the same size as Africa. It is not. In fact, by area, it's about that. It's about the size of.
It's little more than half the size of India.
Right. Things near the equator are made smaller, and things near the poles are made bigger. In fact, does anybody know, for the Mercator projection, if you take the full Mercator projection all the way up to the North and the South Pole, how tall the map is compared to its width? The actual answer to that question is, if you take the full Mercator projection, it's infinitely tall. The North Pole appears infinitely high up at the top, and the South Pole infinitely far down the bottom. We just cut it off to stop it being infinitely tall. At least that's what we do as a coach. I don't know what's the first class test. Serena, how am I doing for time?
Excellent.
Depends on where
Yeah,
the
you're
end
fine,
is.
you're fine.
Unless your talk is infinite.
It's 9:30. We're doing fine. Yeah.
Okay. It's 9:30 now.
Yeah.
Okay, so we were asking, is it possible that we could be wrong? Is it possible we could be wrong about what's a straight line and what's a curved line? And anyone who has ever watched you as you on the map as you fly transcontinental will know that it is possible to be wrong. In the following way: if I want to fly from San Francisco to London, I fly along that line. Why do I fly along that line? It looks like that line is bent. It looks like that is not a straight line. And the airline is therefore taking me on a circuitous route from San Francisco to London. That is in fact an artifact of trying to take a curved space, like the Earth, and squashing it down into a flat map. You will notice that the line from San Francisco to London goes over Greenland. Now, in fact, to convince you that that is in fact the fastest way to go, I brought with me a globe. The globe is in fact has no distortions. It's inconvenient to use for other reasons, but it correctly captures. You curvature of the Earth. And you will notice that if you want to fly from San Francisco to London, it really is the case that the straight line, the shortest line that will take you from one to the other, which we're going to define to be a straight line, still going to be true that objects move in a straight line when not subject to forces. The straight line from San Francisco to London does indeed chop off the bottom of Greenland. In other words, if you believe the Mercator projection, this flat representation of the Earth, was indeed accurate, you would be wrong about what the straight lines are. You would not realize that that line there is in fact a straight line. And this line here, the so-called run line, the line of constant bearing, is not a straight line. This not straight line is longer than this straight line. This straight line is the fastest route from one to the other. It is the route that would be taken by an object that is not experiencing a force. Similarly, to be balanced, I would give a southern hemisphere example. If you fly from Cape Town to Auckland, you fly over the South Polar ice cap. That is a straight line. That is the shortest distance from one place to the other, as you can verify later on the map if you choose. And indeed, it does carry you over the South Polar ice cap. Once again, that is not a straight line. If you believe the Mercator projection, you would be wrong about what you claim is a straight line and what you claim is not a straight line. But let us say that you did only know about the Mercator projection, that your mind was too limited to conceive that the Earth was not flat. If you believed the Earth was flat, but nevertheless noticed that planes were making these strange curved routes, what would your hypothesis be? Your hypothesis would be that there is a force pulling planes towards the equator. That the plane is doing a parabola because it's thrown from San Francisco, and in order to arrive at London, it needs to arc up like a ball being thrown in order to land in San Francisco. And similarly, in the southern hemisphere, there is similarly a force, a fictitious force, one might say, pushing it towards the equator. And so really the getting about equations, the heavy lifting is meant to be done by looking at this diagram and comparing it to this diagram. In this diagram, we said that in order to buy that gravity is an inertial force, Einstein required us to buy that we could be wrong about what straight lines are in space-time. That lines that look straight are in fact not straight, whereas lines that look curved, look like parabolas, are in fact straight lines in space-time. And therefore the forces, the fictitious forces experienced by sitting Einstein, the fictitious force pushing him down to the bottom of his deck chair, is in fact merely an inertial force caused by the fact that he is not traveling along a straight line. And it is clear that in order to be mistaken in that manner, about what a straight line is and what's not a straight line, one way we could be mistaken is in fact if space-time, like the surface of the Earth, is curved. On the surface of the Earth, the curvature of the Earth, if you close your mind and try and cram a round Earth into a square map, you will be mistaken about what straight lines and what the not straight lines are. And if you force yourself to believe that the world is flat, you will have to believe that there are forces, that there are fictitious forces that act on aeroplanes moving on the surface of the Earth. That is in fact the idea of Einstein's general relativity as applied here. that a ball moving through space-time is flat, straight, and somebody sitting down is in fact curved. Okay, and then let me just flash before your eyes the mathematics that that underlies this. This is the central equation. I think this is in fact the 6th equation in the talk. My quota is spent. This is the equation that underlies general relativity. This is the slogan up top. Space-time tells matter how to move. The curvature of space-time tells you what the straight lines are and therefore how matter moves. But in order to affect gravity, the curvature better reflects the fact that there's some Newtonian limit where you see an inverse square. And so for that reason, the matter tells space-time how to curve. And that's what's responsible for the force of gravity. And this is just a famous equation you may have seen, and in fact the sole equation of general relativity, where the left-hand side here is some mathematics telling you about the curvature of space-time. The equal sign tells you that means that the curvature of space-time is determined by whatever's on the right-hand side, and the right-hand side is matter, tells you about how much matter there is. And if you want to understand this equation, let me put a plug-in for this fall. I'll be once again teaching the general relativity course at Stanford. Last semester I had 5 auditors. Everyone is very welcome, and one of them even got an A+, so everybody is very, very welcome to sit in. Let me now just briefly mention why we believe this. That's the idea. Let me mention, that's the sort of the idea part. Let me mention why everybody soon came to believe it after Einstein said it. And the central thing that made people come to believe it was the observation of the bending of light. So Einstein made this theoretical prediction, but he was just some theorist with some idea. In science, if you really want to convince people, it's best if you have a falsifiable experiment. And the falsifiable experiment, actually even before he had finished his theory, in 1913 this first occurred to him, that a very important thing to look at was going to be the deflection of light by the sun. So it's lost a bit at the top there, but there's a star up top, and the light from the star passes the sun, and as it passes the sun, it's bent. It's bent as it passes the sun by the gravitational, what we call the gravitational force on the light, what is in fact the curvature of space-time near the sun, and the light is following a straight line in that space-time, but that causes it to deviate from how it was before. Einstein realized that if he was going to convince people that his theory was correct, this was an important quantity to look at. And general relativity predicts as a factor of 2 larger than the Newtonian deflection. If you ask how does light deflect in Newtonian theory, or how does something moving at the speed of light get deflected in Newtonian theory as it passes the sun, versus in general relativity, the answer is a factor of 2 larger in general relativity. And Einstein realized that this was an important quantity to look at, and so already in 1913 asked the German arms manufacturer Krupp, in which he had good friends, to organize an expedition to go and look for the deflection of light by the sun. In fact, the first thing he did is he went to the director of the Mount Wilson Observatory and asked him about how many stars you could see, how close to the sun you could see stars, in order to be able to observe the deflection caused by the gravity of the sun on those stars. And the director of the Mount Wilson Observatory told him that you could see 0 stars in the sky, and certainly if you look very close to the sun, you can see none whatsoever, because you'd be completely blotted out by the sun. He did, however, make the very good suggestion that there is one time when the sun will not blot out your view, which is during a solar eclipse. And so that started the great solar eclipse race of the 2nd decade of the last century. During a solar eclipse, the moon blots out the sun, and by looking at stars just to the side of the sun, you can, where the sun would be, you can measure their deflection. And so the story actually doesn't really reflect very well on anyone, but this is how it happened. In 1913, Einstein persuaded Krupp to send down a set of people to observe the solar eclipse in Argentina. And they went all the way from Germany to Argentina, which was more of a big deal in those days. And they didn't see anything because just at the last moment some clouds came in and obscured the eclipse, which is in fact also my experience of seeing a solar eclipse in China. And then the next time they went, the next solar eclipse in the world, they looked in their old map, and there was one in the Crimea. So the next year they went to the Crimea, and they were there in August 1914, which was not an auspicious time to be a German arms manufacturer-backed expedition full of observational instruments. And a week before the eclipse, World War I broke out, and the whole of them every single member of the expedition got arrested as a spy. And so they were unable to watch the solar eclipse, and I think spent the First World War in a prisoner of war camp, sitting up an entire day. And then it turned out to be a reasonably good thing for Einstein that all of this had happened. Because it turned out that Einstein had actually made a mistake in his original calculation. Einstein's grand prediction that he'd made before was that, unlike other attempts to modify Newtonian gravity, his theory of curved space-time had no difference whatsoever from the Newtonian prediction. Einstein claimed that his prediction was that exactly the Newtonian prediction for the deflection of light should be correct. And so the First World War came, and during the First World War, he went over his calculations again, and discovered that in fact he was completely wrong, and that in fact his theory predicted double the Newtonian deflection. It would certainly have been embarrassing if that's what the experiments had found, and then he later had to explain that his prediction was incorrect. And then nothing really happened for 5 years. Einstein found his mistake theoretically, but nothing experimentally happened for 5 years, until after the war, until 1919, when Sir Arthur Eddington, a British scientist and pacifist who was very keen to have some kind of post-war reconciliation, went down, in fact, did 2 simultaneous expeditions to observe the same eclipse in Africa and in South America, and observed the predicted deflection of light to be double the Newtonian value. And really, this is the event in 1919. Einstein was certainly physics famous before this point, but this is the point at which Einstein became globally famous. He became a global celebrity. And in fact, this is the New York Times headline the day after it was discovered. The headline you can't see is, "Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations. Einstein theory triumphs. Stars were not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more if all the world could comprehend it," said Einstein when his daring publishers accepted. And this was the event that catapulted Einstein to global celebrity, and also convinced the physics world that general relativity is the correct theory of gravitation, and Newtonian gravity is incorrect, and all the other pretenders are also incorrect. Actually, historical re-examination of the data has not supported that conclusion. Historical re-examination of the data has suggested that Sir Arthur Eddington was extremely keen to confirm Einstein's theory. And if you actually look at his data, the error bars are far too large to distinguish, or the correct error bars are far too large to distinguish Einstein's theory from Newton's theory. Nevertheless, subsequent celestial observations have indeed confirmed that Einstein's theory is correct, and it is now our best theory of gravity to this day. In fact, it's the oldest remaining part of the sort of canonical theories that we have to describe the world. Yeah, let me wrap up there and then take questions. Just let me say, to my mind, general relativity is really, as I said at the beginning, the most perfect theory that we have in physics. The way it all sort of works together, these sort of thought experiments, these beautiful mathematics, and then the fact that it actually turns out to be true about our universe and that we can tell, and that the fact that it's true turns out to be important, otherwise GPS wouldn't work, I consider to be a sort of great symphony on the same magnitude as Shakespeare or the Manhattan skyline or any of these other things, and I think our universe should be honored to be described in it. Say that again?
You said straight line.
Straight line? Yep.
Is that still a metaphor?
Straight line is actually not a metaphor. The notion of a straight line is absolutely central to both the mathematics, the geometry, and the geometry of curved spaces, and also to the physics. Newton's first law and indeed his second law are not changed by general relativity. It is still the case that objects not subject to forces move in straight lines. Now, there is one small question that I sort of elided over a bit, which is the straight lines are straight lines in space-time. They're not straight lines in space. They needn't be straight lines in space. So there's this notion that, let me back up and draw the diagram again. This is actually a space-time diagram. It describes, if you have a point particle, like an electron zipping around, you might think of zero dimension as a point particle, but actually, in physics, we say that it's one dimension. It's got 0 dimensions of space, but it's got a dimension of time, because it persists forever. And so here's a diagram showing it moving through time. It traces out a line, we call it the world line. And it is the question of whether that line is straight or curved is not metaphorical. This is a genuine physical question. And by straight line, I really do mean straight line. In this business, straight lines are sometimes called geodesics, but that's really just a fancy word for straight line, the shortest distance between two points. Yeah.
So it seems all of this is predicated on the belief or assumption that the sun has to be not only moving at a finite speed, but also be universally maximum speed. I'm just curious, maybe you already talked about this, but how did Einstein know that? How did he think that that was maximum speed? I know later on we were able to prove it empirically, but he couldn't at the time. So how did he
Right, so the question is, why did Einstein think that the speed of light is the maximum speed?
Right,
That's your question?
universally maximum.
Right.
Because that's the assumption that, if that's not true, then not this case.
That's right. So there's two questions. First question is the special relativity question, which is how do we know that in non-gravitational physics, the speed of light is the fastest speed at which things move? The second question is how do you know that that remains true once you incorporate gravity? There's a number of answers to that question. Perhaps the strongest motivation for many people was that if you look at the complete theory of electromagnetism, which was written down in the 1850s or 60s by Maxwell, it wasn't put in as an input into electromagnetism, into these Maxwell's equations, just define electromagnetism. It actually was a surprising outcome of these equations that nothing, as far as electromagnetism is concerned, if it's described by Maxwell's equations, can possibly move faster than light. No electromagnetic influence can travel faster than light. Now, as far as Maxwell was concerned, that and others at the time, that was a sort of surprising consequence of Maxwell's equations. Einstein, however, took a radically, this is with regards to special relativity in 1905, long before electromagnetism. Einstein took a radically different perspective that to many of his contemporaries just seemed like cheating perspective when he invented special relativity, which was, again, to move this fact that in electromagnetism nothing moves faster than light, to move it from a surprising consequence of the theory of Maxwell's equations to a central axiom. He just assumed, he said, suppose it is universally true that nothing can travel faster than light, what would follow? So that was really a sort of intellectual leap that Einstein made that many other people at the time hadn't made and considered to be cheating. You couldn't just assume it. But that is sort of where he came. So there was the observed fact of electromagnetism, and also the observed fact that nothing had ever been seen to move faster than the speed of light. But there was also just the suppose it is true, what follows.
So it's more of a prediction, and then the
I mean, it was both a prediction and a post-prediction. Electromagnetism had already, if you believed electromagnetism, at least as far as electromagnetism was concerned, it had to be true. But it was also a prediction for the future that nothing else in the future would be found that would violate this. Yeah.
Thank you for the talk. It was very inspiring. You made a wonderful job in showing the difference between electrostatics and gravity in terms of like the charge corresponding to the force law.
Yeah.
And so, hinging on that, how do physicists feel about the difference between gravity and the three other forces? Because the three other forces have their own intrinsic force charge, which is different from the inertial mass. And gravity has this special thing where it falls exactly equal. So is this really a force, or is this how the kinematics of space-time work? So, I mean...
Yeah, so as you say, there are four forces. I mean, these are what are called the four fundamental forces, but really there's sort of 3 plus 1. These three both have this plus sign rather than the minus sign, and also don't have this equivalence principle fact for all three of these forces. So the two essential differences of general relativity are of gravity, and number one, that like charges attract rather than repel, and secondly, that the charge is proportional to the inertial mass. And that means that gravity is different. This trick that we did with gravity, where we explained gravity as being due to the curvature of space-time, and we really turned it into a fictitious force, like the centrifugal force or the Coriolis force. This trick where we were able to say, suppose space-time is curved, that would explain this. That same trick won't work for the other forces, at least not without considerably more mathematical sophistication.
Yeah, so that might explain, not explain, but hint at why they can't reconcile general relativity with the three other quantum.
Well, let me stop you there. The three other forces and general relativity are 100% perfectly reconcilable until you introduce quantum mechanics. The traditional problem of quantum gravity is the problem of taking these theories, all of them, and adding quantum mechanics. Just at the level of not having quantum mechanics, before you have quantum mechanics, there is no contradiction between these. We can describe gravity with electromagnetic and strong and weak forces running around on the back of it. The hardship is when you introduce quantum mechanics. There we understand very well what to do with electromagnetism, strong force, and the weak force. We do not understand what to do with gravitational force, or at least many people think they do. Through string theory is a leading candidate for what to do about it, but it is definitely not a settled issue. Yeah.
So you talk about the apparent perfection, relative perfection of Einstein's theory. If we know that there are difficulties reconciling gravity with the other forces in the quantum arena, and we know that there are these singularities that you can't get rid of with Einstein's theory, could we turn this around and ask whether this is actually the great screw-up of the 20th century, that this particular theory appears perfect prematurely, and therefore we can't easily figure out what to do because it doesn't allow for elaboration? Could it be that Einstein has effectively trapped us by giving us something that appears to be perfect but clearly needs to be superseded, and therefore we can't come up with the thing to which Einstein's theory is the approximation?
Good. Yeah. So I think I basically agree with the factual basis of your question, which is, I just mentioned that there is a tension once you get to the quantum level about how to understand how quantum mechanics, the two great early 20th centuries of physics, really the two reigning paradigms that we have, are general relativity, which explains gravity in terms of the curvature of space-time, and quantum mechanics, the theory of the very small. Usually, and they seem to be in tension. Usually we don't worry about that too much, because quantum mechanics describes tiny things like atoms and molecules, or at least that's where it makes its effects most felt. Gravity describes planets and indeed the expansion of the whole universe. And they have their sort of non-overlapping magisteria where they describe these two different regimes separately. Nevertheless, it is not at all clear how to combine quantum mechanics with general relativity. And it seems one of them has to give. At least one of them has to give. According to my favorite theory of quantum gravity, which is string theory, the one that gives is gravity. Quantum mechanics, in that theory, turns out to be absolutely correct, including in string theory. Gravity, by contrast, gives. It turns out that while this beautiful geometric description of space-time given us by general relativity is true at long scales, when you get to very, very short scales, it's no longer true. You get this, well, first you get a sort of space-time foam, where space-time is fluctuating wildly due to quantum fluctuations, and then eventually the whole, if you get small enough scales, the whole space-time description breaks down entirely, and you need to move to 11-dimensional strings. Yeah, I would agree with that factual basis for what we just said. Your now question was, were we beguiled and seduced wrongly by Einstein? It seems as though Einstein wrote down the best possible theory one could ever conceive of at the beginning of the 20th century. As we move into the 21st century, we have to understand its strengths and its limitations. Does the myth of Einstein, is that a destructive myth? It is to a certain extent. This doesn't really happen in theoretical physics. Quantum mechanics, or indeed any of these other forces, were the work of many hands. This business where just one solitary genius sits down and figures out general relativity is the some sort of Ayn Rand novel sort of comes alive. It hasn't really happened very much in any other realm except for general relativity, and maybe it's given people who just focus on this a misleading picture of how physics is usually done. I mean, even general relativity, Einstein had help, but it was definitely a singular vision. Yeah.
You said nothing being explored faster than speed of light. The expansion and contraction of space, which we interactively and described, can happen faster than speed of light.
Good, so let's back up. General relativity, as well as describing the motion of planets, also describes the evolution of the entire universe. The universe, we believe, is expanding. If you look backwards in time, it's contracting. It comes from a Big Bang, and then it sort of blows up from a Big Bang 13.8 billion years ago, as precisely described by this formula here, that tells you about the expansion of the universe in response to the matter that lives inside the universe. And everything blows up, and the universe gets further and further apart. And in fact, it can become the case that it is impossible to send a signal from one place to another. And in that sense, the universe is expanding faster than the speed of light. If we look at stars that are currently about 20 billion light years away, and imagine them sending light towards us that leads them right now, that light will never reach us. The expansion of the universe will rip us apart faster than light can ever reach us. And your question is, how is that consistent with my statement and with Einstein's statement before me that nothing can travel faster than the speed of light? And the answer to that question is that the rule is that velocity is only determined by things that are moving past each other. It's only locally determined. In fact, general relativity doesn't even really make sense to talk about the velocity of two objects that are not at the same point. You only get to measure velocity as two things pass. we and those other stars, it's not even really well defined what our relative velocity is, because they are a very long way away from us. So the rule is that two things that are passing each other can never have greater than the speed of light. Two things that are well separated, like us and that star, it's not even really well defined what our relative velocity is. If it was well defined, I'm not sure it would be fair to say that they're moving faster than the speed of light. Instead, I would say that they're moving less than the speed of light, and they emit light towards us, and the light is moving locally at the speed of light. It's just that space-time between us and those stars grows faster than it gets gobbled up by the light moving in. Okay. Yeah?
Yeah, I had a couple of questions.
First one.
It's all about quantum mechanics. Yeah, this whole spooky aspect. And with quantum entanglement, theoretically, you can observe information at great distances at a rate faster than the speed of light, right? So how did he go about saying that light is the fastest thing? And does that affect anything else here at all? The second question was, do you know anything about the theory of gravitational waves, and what is the speed of gravitational waves?
Okay, let me take those two questions. The first question was about quantum mechanics, specifically quantum entanglement. Einstein not only knew about it, he discovered it with his collaborators Widolsky and Rosen in the 1930s. And the question was, is it possible, using entanglement, to violate the speed limit, to send information faster than the speed of light? And the answer is no, it is not possible to do. In quantum mechanics, there is quantum information theory. There is an effect called the no signaling theorem that tells you that nothing, that you cannot build a telephone, essentially, using quantum mechanics. You can't build a telephone that communicates faster than the speed of light. Nothing you can measure or wiggle or anything you can do over here can possibly affect the other side any faster than the light timing and light travel time from one side to the other. Nevertheless, there is some correlations that can be set up that if you wanted to explain quantum mechanics in terms of a hidden variable, it's called a local hidden variable theory, would require faster than light communication. This is, I think, a great example where physics is ahead of philosophy. Philosophy and communication theorists had plenty of opportunity to come up with, imagine a possible world in which it was possible to influence something that was a long way away without being able to send any information. And so the quantum mechanical correlations are precisely of that nature. There is this no signaling theorem that tells you that it's impossible to send information faster than the speed of light. Nevertheless, something has happened. But whatever that has happened makes it impossible to build a telephone that travels faster than the speed of light, and therefore does not violate special relativity. The second question was, how fast are gravitational waves? And the answer is that gravitational waves move at the speed of light. It's the short answer. What are gravitational waves? Gravitational waves are to gravitational fields as photons are to electric fields. Gravitational waves are like the excitation of the gravitational field. They are ripples in space-time. And whenever you start moving stress energy, for example, if you have the Earth orbiting the Sun, it'll start emitting gravitational waves. It'll emit a little bit of its energy. The Earth orbiting the Sun only emits a tiny, tiny, tiny bit of energy. It emits such a small amount of energy that the distance from the Earth to the Sun moves less than the thickness of a proton each year, due to the energy emitted in gravitational waves. Nevertheless, you can imagine considerably more violent collisions that would give rise to gravitational waves. Classic example, you have neutron stars, binaries, two neutron stars that are orbiting each other, maybe a neutron star and a black hole that are orbiting each other, or maybe two black holes, and they come in and they spiral in, and now they're going really fast. Maybe they're orbiting each other every second, or even faster than that. They spiral in and then they collide. And when they do that, they emit a truly extraordinary amount of energy in gravitational waves. They emit, in fact, they are brighter when they collide than everything else in the universe, including all the stars in the sky, except that they're emitting their energy not in photons, but in the gravitational equivalent of photons, in gravitational waves. These gravitational waves, just like photons, move at the speed of light. And there was a rumor yesterday about them. We have never observed gravitational waves, but we're looking. And one of the places we are looking is in This one is in Louisiana, and this one is in Washington State. And those are ginormous interferometers. So they send out a laser in one direction and a laser in the other direction. This is kilometers length scale. And the laser goes and it bounces off a mirror and then it comes back and then it keeps going and going and going. And what it is doing is you are interfering these lasers, these incredibly precise lasers. These are just exquisite experiments that I don't have time to tell you about at all. That are measuring ripples in space-time. They are measuring tiny, tiny deviations in the distances. If one arm just becomes a tiny amount longer than the other arm, they will see it. And by tiny, I really mean tiny, like much less than the thickness of a proton, much less than the thickness of a proton. Differences in the length of the photons induced by passing gravitational waves. Of course, those differences won't just be caused by passing gravitational waves, they'll also be caused by passing cars or passing airplanes. Literally, the gravitational field of a passing aeroplane is enough to sort of overwhelm the signal here. Or mini earthquakes, or just about anything that you could imagine. You just better hope that an airplane doesn't pass in Louisiana and in Washington at exactly the same time, and in exactly the same manner, which is why you build two of them. Yesterday, there was a rumor that they have seen something. It is not totally implausible that they have seen something, for two reasons. One is that a few months ago, they just turned on again. They were off for a long time, and they did these massive upgrades that are now 1,000 times more sensitive per day than they used to be. So, one day will take more data than years running previously. And so everyone has sort of been expecting that they might see something. And really, if you make an estimate for how many inspiring neutron stars there are in the galaxy, and what background that would give you, and you look at their sensitivity, it really seems pretty sure, or not unlikely, that they are finally going to see this thing, gravitational waves, soon, maybe very soon. The missing piece of Einstein's theory. This is like, Newton certainly can't do this. Newton cannot do gravitational waves, and they move at the speed of light, and we may be going to find them. The rumor yesterday is we found them. I wouldn't believe that too much, and I have a reasonably high prior that we're going to find them. But in order to do sort of dry runs, the director of the facility sometimes sneaks in fake signals into the data just to test that everything's working. So even if they think they've seen something, it may be that the director's just going to say, actually, we didn't have it in their hand. But coming, maybe, I mean, even if this isn't it, we're going to see it soon. It's going to happen. Yes?
Why do gravitational waves travel only as fast as the speed of light?
That is baked into General Relativity. I mean, in fact, it was one of the motivations of General Relativity, was that we should ensure that nothing can travel faster than light. I mean, otherwise you could build a telephone using gravity. And one of the points of General Relativity is that you couldn't build a telephone using gravity. If I could wiggle my neutron star over here and send a signal that was going faster than light, then I could build a telephone that communicated faster than light using gravity. And that would be inconsistent with special relativity, and it's also, it turns out, inconsistent with general relativity. Some more profound answer, I don't know why. Yeah, that's why.
But it falls out of the math that we're maybe not seeing here?
It falls out both of the motivation for the mathematics and then out of the mathematics, yes.
Okay.
In fact, the subject of gravitational waves is a... Einstein thought some very funny. A lot of people have thought some very stupid things about general relativity down the years. It was actually a bit of a backwater for its... I mean, it was an initial excitement of the first decade, and then it sort of fell into disrepair and sort of got taken over by some people who weren't very good. And then people just kept on saying stupid things about it. Like, it took people 50 years to figure out that nothing funny happens at the horizon of a black hole, even though from a modern perspective that's just blindingly obvious. Gravitational waves is really, lots of very smart people have said some very dumb things, including Einstein himself, who vacillated on the existence of gravitational waves. He wrote the canonical, well, first of all, he said that they didn't exist in his theory. And his reason for them not existing was that while there are positive and negative electric charges, there's only positive gravitational charges, and therefore you couldn't have gravitational waves. That argument doesn't make any sense. Then in 1916, he said there were. He wrote a paper discovering them. Then in 1936, he wrote a paper 20 years later, saying, whose title was, "Are there gravitational waves?" And if you read the paper, the answer was no. Then he sent it to Physical Review journal, still a journal in physics, to be published, and they sent it out to a review, and then the reviewer came back and said, this is total nonsense, this is what's wrong with it, ABC, correctly, this is what's wrong with it, ABC. Physical Review then sent it back to Einstein, and Einstein just went mad. He said, I sent it to you to be published, not to be reviewed. How dare you send it to somebody without my permission? I sent it to you to be published. I'll never publish in Physical Review ever again. And in fact, he never did. He never published in Physical Review ever again after that day. However, it turns out that the reviewer was 100% correct, and Einstein was completely incorrect. And there were gravitational waves. And then the great cosmologist, Robertson, went to speak to him sort of privately in person and managed to persuade him that in fact gravitational waves do exist. And so in fact he submitted another paper the following year called Do Gravitational Waves Exist? This time the answer to that question was yes. Maybe he was hoping the same title, I don't know what. And much later it has turned out that in fact Robertson was the original reviewer. This was only about 2 years ago, who had in fact rejected his paper. And his review, which is available, is 100% clear and correct and totally nails it, but clearly Einstein was not used to being challenged by that stage of his career and never published in Physical Review ever again. And then, I mean, the madness continued for decades. I mean, the question of whether gravitational waves can carry energy, which they very definitely can, continued into the 1960s and 70s, which is quite extraordinary. Yeah?
When you talked about the star that's moving away from us, and it might happen that the light traveling from the star towards us will never reach us, you said it's not really because, or if I understood it correctly, it's not because the star is actually moving away that fast, it's because the space in between us is expanding. Could you go into more detail on that? Because that's the only reason why that doesn't violate the speed limit of light, right?
Yeah, so as I mean, there are 2 points. One of which is the sort of weaselly technical point, and one of which is like the encouraging you have to think about it better point. The first point is the speed limit only applies to 2 objects that are moving that are coincident. You can only measure somebody's velocity in a curved space. You can only reliably measure somebody's velocity as they pass you. Talking about your velocity relative to something that's a long way away no longer becomes well defined because it's sort of, it becomes path dependent. Like how even I move that object over here will affect its velocity when it reaches me. So for that reason, it's just not a well-defined question. How fast is that star moving away from me? Quickly, it's not well-defined, so it's not, couldn't possibly be a problem. Now here's the second thing, which is how to think about it better. The canonical example that is used to try and have you think about this better is to imagine the stars to be on the surface of a balloon that you're blowing up. It is not that the stars are sort of moving relative to the balloon, rather it's that the balloon is, the surface of the balloon, the material of the balloon in which the star is embedded is growing. It's getting longer, it's stretching, and getting bigger and bigger and bigger. Really, this isn't something you need to spend. Yeah. Let me just leave it at that. That's the correct way to think about it, is that these stars aren't really moving relative to us at all. They're sort of sitting, they're co-moving with us, and this space-time is itself getting expanded.
I'm trying to understand gravity as fictitious force, but if I think about a stationary object, it does fall towards another one. Doesn't that imply it is actually subject to some force?
So the statement would be, if you had a free-falling object, what we call a free-falling object, let us say the International Space Station as it orbits the Earth. To us, it looks like it's moving in a circle. Or if you imagine it as a space-time diagram, it would look like it's moving up in time and it's moving in a corkscrew motion as it goes up. General Relativity tells us that it is in fact not moving. The corkscrew looks bent. General relativity is in fact, it tells us that it is in fact not bent. That in fact, that is a straight line. This corkscrew is a straight line. It only looks bent to us because we have a flat space mindset, just like people using the Mercator projection. And we are trying to cram this curved space-time, project it into a flat space way of thinking about it. And when you do that, we saw that things that are straight end up looking curved, and things that are curved end up looking straight. In fact, the International Space Station orbiting the Earth is quite a fun example, because there, from a Newtonian perspective, you could say there are two forces. There's the centrifugal force pointing out, and the force of gravity pointing in. And those two forces happen to balance due to the miracle that inertial mass is equal to gravitational mass. In fact, Einstein says both of those forces are fictitious forces. You are balancing two fictitious forces against each other, and the International Space Station is following a dead straight line. So, I mean, you're getting... Some people don't like the word fictitious force, and I'm probably amongst those people. So is the centrifugal force a fictitious force? Well, if you're in a car being thrown against the side of the car, it doesn't feel like a fictitious force, it feels like a very real force. The reason it's called fictitious is that it's there because you are choosing to define your motion relative to an accelerated frame of reference. And that if you chose a truly non-accelerating frame of reference, you would see that it is in fact merely the result of not walking on a straight line. Yeah.
So the symmetry, the idea that inertial and gravitational mass are the same is really cool. And we can reinterpret the so-called force of gravity as not a force at all. It's just this space-time that's warped by mass. That's very nice, but how does that, what's the connection between that and the notion that nothing can travel faster than light? They seem like completely unrelated ideas.
That is right.
Did one help Einstein to find the other, or?
Yeah, I would say that these were two joint motivations for Einstein. The first one tells you that there is a problem. The second one suggests a way through. The first one tells you that this theory, as written down, is inconsistent with the principles of special relativity. That it is consistent with the statement that nothing can travel faster than light. This observation of Einstein says, okay, we're going to need to modify gravity somehow. How can we do it? And people just, when people realized that maybe this needed modification according to special relativity, they just started writing down anything. And they wrote lots and lots of papers, and none of them really made any sense. Einstein said, what if we don't just randomly write things down on a piece of paper? What if we take very seriously this idea? So that was Einstein's intellectual development, was there is a problem. In trying to solve that problem, what if I took this very seriously and took it as a guiding principle? And then it turns out that when you do take this very seriously, you also solve this problem. But it's true that it doesn't, just looking at the equivalence principle, it's certainly not immediately obvious that this is going to be help with this. Like, this might be an interesting fact, because this obviously going to help with that. There are some thought experiments that will eventually persuade you that it will help, but I'm not going to go into it. Just this statement, I mean, then we can start doing thought experiments and see that it's actually going to help. Yeah.
You said that initially Einstein predicted that the same deflections would be observed as being. So why were they doing expositions?
Good. Yeah, so the answer is that there were other people in the game. Everyone else's theory is basically terrible, but there were other predictions, and those other predictions a non-Newtonian.
Oh, right.
Did anyone predict 2?
No one else predicted 2.
Yeah.
Serena, are you here?
I think she just said that.
Okay. I'm happy to sit here and take questions all night.
Sorry.
Serena,
I'll just, yeah.
how do you want to?
I think.
I mean, if you just want to drift away, that's fine by me. But if no, I'm happy to.
I think what the best thing to do is to like let everyone have a drink and maybe talk to you.
Okay.
Yeah. So there's